AS1 Physics 1, and it's June 2008 question 5. Okay, and we have here to sketch two graphs, one for a uniform metal wire, the other for an NTC thermistor, and how they depend on temperature. This one here has come up several times over the years. In fact, I think it was in January 2008 as well. It's an increasing straight line with a positive intercept because it does have a resistance at 0. So it's really important. It starts there and it goes up in a straight line. The NTC thermistor then starts off with the resistance and falls down and becomes asymptotic to the axis. Probably not maybe at 50 degrees Celsius, but it comes down like so. Then we have a long conductor for an electric railway is to be made from a length of material of uniform cross section. Distinguish between the resistance and the resistivity. Well, first of all, resistance is a property of the conductor. So resistance is a property of the conductor. And depends on the dimensions of the conductor. And depends on its dimensions. Whereas resistivity is a property of the material and depends on its atomic structure and not its dimensions. Possibly worth adding in there that resistance is measured in ohms and resistivity in ohm meters. I'm only saying that is because in a previous question there were marks given for that, so it would be possible to just go and add that into there if you wanted. Right, so we now have two materials A and B available to manufacture the conductor. They have resistivities of 1.6 times 10 to the minus 8 and 5 times 10 to the 16. The conductor is 2.3 long and of cross-sectional area. Select a suitable material and mark your choice by placing a tick in the appropriate box. Calculate the power dissipated in this conductor when the current through it. Well, we're looking here at the resistivity, so we're looking for one which has got a very small resistivity. So material A is 1.6 times 10 to the minus 8. This is material B, 5 times 10 to the 6. So material B has got a really high resistivity, so you wouldn't be choosing it. So we're looking for one which has a low resistivity. So we're going to put a tick in beside A because that's the one that we want. And then we're looking for the power that's dissipated in that. Well, first of all, we need to work out the resistance. So the resistance is equal to rho times L over A. So that's equal to 1.6 times 10 to the minus 8 times the length was 2.3 kilometers. So that's 2.3 times 10 to the 3 meters. And is a cross-sectional area of 50 centimeters squared. Okay, so we need to be careful there because it's 50 centimeters squared, so that's 50 times 10 to the minus 4 meters squared. And that, when we multiply that out and calculate that, turns out to be 7.4 times 10 to the minus 3 ohms. So that's the resistance. To work out the power dissipated, we're going to use P is equal to I squared R because we've just got the resistance. So if we know the current, which we do, up here we're told is 44 amps. Therefore, P is equal to 44 squared times 7.4 times 10 to the minus 3. So 44 squared, that's going to make a significant input into that, but we're multiplying by 10 to the minus 3. Put that into your calculator and that turns out to be 14.3 watts. So the power dissipated is equal to 14.3 watts.